Okay, so as we have seen in the previous part, okay, after implementing the code, after implementing the formulation, like the mixed formulation for 2D Stokes flow, okay, using the 4-node element, okay. So we have seen these spurious oscillations, okay, and also if you notice the output here, the matrix similar to machine precision. So the R condition, like condition number, so it is 2 point something e power minus 22. So that means the Jacobian, the determinant of the Jacobian is 0. Okay, so it is like it's difficult to find solution for this problem, and one of the reasons is like, and that is one of the reasons why we get the spurious oscillations. Okay, and refining the mesh doesn't help. Okay, so I have a finer mesh, okay, a 40 by 40 mesh. Okay, so it doesn't help. We still have these spurious oscillations, although not as pronounced, but we can still see that the pressure value, you see, from minus e power 18 to like plus e power 18, and we can see these oscillations here. I hope it doesn't crash. Yeah, okay. So like you see, there are still some oscillations. Okay, so why do we get these oscillations? Okay, so bear with me now. Okay, so in order to understand why we did these oscillations, okay, so there is a lot of math behind this, but like it's a scary math. Okay, I'm going to be honest. Okay, but we don't need to know all that scary math to understand these oscillations and get rid of them. Okay, so in order to understand this, first like we need to know what this inf sub or LVB stability is. Okay, so our discrete system for study Stokes. Okay, so this is our matter system. Okay, so KPP is 0. Okay, so this is called a saddle point problem. Okay, this is the problem that we usually encounter in optimization problems. Okay, so where we have a constraint, which is what we have now, the divergence of velocity is 0. It is a constraint, and we are using Lagrange multiplier like to solve this constraint optimization problem. Right, okay, so and because of this 0 we end up with a saddle point problem. So what do we mean by saddle point problem? Okay, so if you look at the horse, like when, so we have the saddle, right? So one, and in one direction it is going down, and the in, so okay, going down and going up, and in the other direction it is going up and then going down. Yeah, so I have the picture to better show it. Okay, so okay, so in one direction it is going up and then going down, and in the other direction it is going down and then going up. Okay, so this is a saddle. Okay, so what is the connection here? So the connection is, so the spaces that we need to choose for U and P should be such that, okay, so the space should be at this point of intersection. Okay, so this is the maximum point along this direction and minimum point along this direction. So until our spaces do not satisfy this criteria, this is like LBB stability condition, we get oscillation. Unless we have U and P spaces selected such that this criteria is not satisfied, then we get oscillations. Okay, so like I said, P acts as Lagrange multiplier enforcing this constraint. This divergence of velocity is 0, and because of this we can't choose our like elements or element spaces for velocity and pressure arbitrarily, which is okay, that means we cannot choose them the same. Okay, so which is what we did. That's why we have oscillations. Okay, so these spaces for U and P should satisfy this inverse stability condition. It is also known as the Lady-Jenstra-Bobustra-Bridge condition, LBB condition in short. Okay. Okay, so what does this mean? Okay, what is the bottom line? Okay, so okay, so before we go there, okay, so this is the inverse stability condition. Okay, so infimum, supremum, infimum in P, supremum in U. Okay, and this is the condition. Okay, so this is the like the expression. Okay, so integral of P over P multiplied by divergence of U, the integral of this over the whole domain divided by norm of U and norm of P. So that should be non-zero, and this beta should be it, and this beta. Okay, so it should be a constant. Okay, so beta is the constant. Okay, and here so we have UH and PH. This is just to represent that UH and PH are the discrete versions of our continuous variable U and P. Because when we describe the space using finite element approximation, we don't have the continuous variables anymore. We have the discrete variable. We have their corresponding discrete versions. Okay. So here, strictly speaking, this UP are like UHPH. So in order to avoid like writing UH all the time, so like we write U and P. Okay. So this condition, okay, so it's a scary maths. Okay. So infimum in P, supremum in U in that space, and in this integral and all. Okay. So this is our okay. This is sorry, yeah, this is our LBB RM stability condition. So like we have to choose the spaces U and P such that this integral, this whole expression is a constant and greater than 0. And if like for us engineers it's difficult to understand, so what fortunately what we can do is we can rewrite this and it becomes an eigenvalue problem, which is easier to understand. Okay, so Chapelle and Bathe has the InfSub test to test the different element combinations and to see if they are stable or not. So what we do is like we calculate eigenvalues for different combinations of U and P, and we can then prove numerically if the element is stable, the combination is stable or not. So I have it in my papers. So if you want, you can refer to my papers. But yeah, at this point, if you think it's beyond you like your comprehension, that's perfectly fine. Leave it. Okay. Now, okay, what is the bottom line? The bottom line is we cannot choose U and P arbitrarily. We have to choose them such that U and P satisfy the LBB condition. So that means we are restricted in what we can choose. Okay. So as we have seen, we cannot choose U and P the same because it violates the inverse stability condition. So there are few options that we can use. Okay, so if we were dealing with the triangular elements, so we have what are called as Taylor Hood elements, and there is another famous element called mini element. Okay, so in the mini element we have a 3-node triangular element added with a bubble, qubit bubble. So this is why it's called P1B. So we use this for the velocity space and our 3-node element for pressure space. Okay, so like P1B, P1. And in Taylor Hood elements, we have Pk, Pk minus 1, that is 6-noded element for velocity and 3-noded element for pressure. So basically what we have here is the pressure space should be one order lower than the velocity space. Okay, so Pk, Pk minus 1. These are all the continuous pressure elements, and we can also have discontinuous pressure, that is element wise. You can see the difference here. So I have these pressure nodes at the corners at midpoints, whereas here I have them inside the element. That is, for each element we have separate degrees of freedom so that we can achieve discontinuous pressure. We do need it sometimes. Okay, and this is for like, okay, so this is for triangular elements, and we have very like similar like combinations for quadrilateral elements. So like we have no, okay, okay, so this is not correct. Let me remove that. We don't have many cubic element here. So it is possible to derive mini element like or equivalent mini element for quadrilateral, but it's not really worth it. Okay, so in the Taylor-Hood family, okay, we have this family of elements. In the Taylor-Hood family, we have Qk minus 1. Okay, so for example Q2, Q1, that is quadratic for velocity and linear for pressure, cubic for velocity and quadratic for pressure. Okay, here these are all continuous pressure, and for discontinuous pressure there is this odd element Q2 P1. So P1 means like the triangular approximation within the here. So P1 is triangular approximation, but we use it within the quadrilateral domain. It's a bit odd, but mathematicians like it. Okay, so this is how we avoid the like this is how we satisfy the insubstability condition. Okay, so by choosing this element like this. Okay, its implementation is little bit difficult. Okay, I will show it how to, I will show how to implement it in the like next parts. Okay, so this is one option. Okay, so this is why like one option in the sense this is why we get spurious oscillations if you use the same spaces for velocity and pressure, same element spaces for velocity and pressure. The option is like one solution is to use different spaces for velocity and pressure and making sure that they satisfy the insubstability, and these are the elements that do satisfy the insubstability, but their implementation is a little bit tricky, and the solution is also like gets computationally expensive as we go to three-dimensional problems. Okay, now what is the alternative? The alternative is that is the alternative to using different spaces. So if you want to use the same spaces, so what we need to do is we need to add some stabilizations to circumvent these instabilities. Okay, I will come back to the, okay, so these are the textbooks you can refer to if you want more information about insubstability and mixed formulations and mixed elements for incompressible flows. Okay, we will come back to insubstable elements later in the next parts. Okay, so if you want to use the same element spaces for velocity and pressure, what we need to do is we need to add a stabilization. So this stabilization is called pressure stabilization. Okay, so what we do here is, okay, on top of our weak form, okay, so this is our weak form for the momentum equation. So this doesn't change because the zero diagonal is from the second term, that is the incompressibility constraint. So what we do to the second equation, the width to the weak form, we add an extra term. Okay, so here tau is our stabilization parameter, and this term, okay, so this is very similar to the SUPG term that we have added, right? Remember, so okay, in the convection equation, so to stabilize the oscillations we have added the streamline upwinding, so where we take the derivative of the variable multiplied and then multiply it with the residual. Okay, so this is exactly the same. So here, so what we are doing, so we are taking the derivative of q and multiplying with the residual of the momentum equation. Okay, this is the stabilization term. Tau is the stabilization parameter, so del q is the gradient of q. Then this is our the expression inside the bracket is our residual of the momentum equation. Okay, and it's equal to 0. Okay, so this gives us extra terms, okay, in this difference matrix. So similar to our distillation of U and P, okay, and U and W and Q, okay. So we can distillize delta Q, like del Q, okay, the gradient of Q, okay, and gradient of P, okay. So we need gradient of P as well, okay. So we have this gradient of P. Okay. Now here remember we do not transfer the derivatives. We do not do apply the integration by parts and divergence theorem, because we already have a derivative for Q here. Okay, so we use it as it is, and for linear elements this is the second derivative and it is 0 for linear elements, so we can simply ignore this. So we have only del Q multiplied by del P and del Q multiplied by F. So we have two terms, extra terms. So for that we need del P and del Q. So this is del P and we already know the basis functions for P. So NP1, NP2 and so on. And by writing in this fashion we have our gradient matrix for P. And since we use the same approximation for Q, we have del Q equal to GPQ. Okay. And then by substituting this distillation into the weak form, okay, we get the pressure stabilized Petro-Delaarkin formulation. And like in the global, like the blood matrix is the same, except that now our KPP is not 0 because we have the term del Q multiplied by del P, okay, which is like a I don't know why I have my hand. Okay, so let's forget that. Okay, so now here KPP is no longer 0 and it is given by, okay, tau. So once we substitute del Q, we have the this business of transposes and all, vector notation and all. Okay, so we get GP transpose GP. Okay, and for FP we have extra term because we have F. If F is non zero, we should consider this contribution. Okay, so this is FP. Okay, so this is a stabilized formulation and it helps us use the same basis function, same element for a velocity and pressure. Okay, now so what is the change in the stiffness matrix calculation? So we need to add these two additional contributions to KPP and FP. Okay, and of course we need to calculate our stabilization parameter tau. Okay, so the stabilization parameter tau, like there are the variety of expressions for tau. Okay, the simplest one is this He square divided by 4 mu. The He is the length scale, characteristic length of the element, and mu is our viscosity parameter. Okay, so it, like now that we have already implemented the stiffness matrix for the same basic functions, okay, so we can simply go back and add this KPP and FP. Right, okay. So what we need to do, so we go back to our stiffness matrix. Okay, so here we already have GP. So here first what we need to do, we need to calculate tau. Tau is He square divided by 4 mu. Okay, so He, okay, we can calculate it from the area. Okay, if I go back to the 2D advection diffusion equation where we calculate the area and then get the length scale, element length scale. Okay. So here, so what I need to change it to okay. Now we don't have a x1 y1 x2 y3, but we have array x node y node. So I'm going to change this. Okay. So first I calculate the area and then I calculate the equivalent diameter of that area. So pi by 4 d square or pi by 4 h square equal to this area. Okay. So and then so we calculate h. Once we know h, we then calculate tau. Okay. So now we have all like since we are using the same basis functions, so our derivatives of basis functions in P are the same as basis derivatives of basis functions in U. Okay, so we don't need to recalculate. So we can use the same derivatives and then populate into the GP matrix. Okay, so one we have this and then so what we do, so KPP equal to KPP plus tau GP transpose GP d volume. Okay, and then FP equal to FP plus okay, so FP plus tau GP transpose F multiplied by d volume. Okay, right. Okay, so that's all we need to change. Okay, we need to calculate tau and we need to calculate GP if we didn't calculate before, and then add the contributions to KP and FP. Okay, now let's see what happens. So let's start with our course mesh. So here we don't need to change anything else here. Okay, so that is why okay, so we have already like completed everything, so we assemble it and all. Okay, let's run it. Okay, change. Okay, now you see the pressure is smooth. Okay, it is between minus 20 and plus 20. The pressure profile is really smooth. Okay, and if I use a finer mesh, it should still work. Okay, so yeah, the pressure profile is still smooth. Of course, the values get bigger because like at the corners we have singularity. That means the theoretical value is infinite. Okay, so as we refine the mesh, the value keeps getting bigger and bigger. But the good thing is the pressure profile is smooth. That is, it is free from spurious oscillations. Okay, and we can also check the velocity. Sorry, so velocity plots. Okay, so in the solution we store okay, not okay. We store the velocity x velocity y velocity x velocity y velocity like that. So I start with the first value and then I take a stride of 2 up to velocity degrees of freedom. Okay, so this is our x velocity. So here we have you see this is our profile. So here okay, so this is our profile. If you want, you can vary the value of a and see like how the profile changes and all. Okay, so this is x velocity, and we can similarly plot y velocity by starting at 2. Okay, so this is y velocity. Okay, just to check what happens to the velocity in case like we didn't check this. So the velocity field without stabilization. Okay, so this is pressure field. Okay, so again, so like even in velocity we have spurious oscillations. Okay, without stabilization. By adding the stabilization, okay, we get rid of the oscillations in both velocity and pressure. Okay, so this is pressure, this is velocity. Okay, so yeah, so that is how we get rid of spurious oscillations by adding the stabilization while using the same basis functions for velocity and pressure. One of the primary reasons this has become popular is of the fact that we can use the same basis functions for velocity and pressure and it becomes easier to code, and also we get non-zero values in this diagonal in this, okay, KPP. It becomes like we can use iterative solvers which are much more like computationally efficient for 3D problems. Okay, so yeah, so this stabilization formulation is quite powerful. Like we can use the same for Navier, of course. So if you look at my GitHub, so I have this parallelized code and using iterative solvers we can solve 3D problems. Okay, so with millions of degrees of freedom on like hundreds of crores. So that's one way of getting rid of spurious oscillations, and this is an easier way and it is also computationally efficient way. Okay, and in okay, so in a similar fashion we can like use the different basis functions like the same code, like you can extend it to use like triangular elements, okay, or higher order elements. The stabilization still works irrespective of the order and type of the element. Okay, you can try it if you want, like it will be good as an exercise for you. Okay, so in the next part and next and last part I'm going to show like the implementation for LBB stable elements. So you can implement it on your own. All we need to do is like we don't need stabilizations, but we need to change the velocity degrees of freedom. We need to choose different orders. It can be a little bit tricky. So in the next part I'm going to show how to do it.